So chapter 11, the vectors chapter, there's lots of little bits and bobs in this chapter. Really, I'm going to advise you to make sure you've read through it carefully and you've got all the kinds of questions out of it and all the bits of information you need from different places. That said, I'll try and cover all that in these videos, and there's a few things, hopefully, which I can add which will be useful. So first of all, if you have a line, then it has a length, okay? So that's a line of length 5. This is also a line of length 5. We can think of a line as an amount, and there's no direction involved, okay? So if I took that line and I moved it like this, it's still got a length 5, it's still got a length 5. Wherever the line is, it has a length of 5, okay? So the size of that line is a 5. If I take a line and I put an arrow on it, and I say, well, that is a length 5, but it's going that way, then now that has a size, a magnitude, and a direction. So if I move this paper around, this line, the only thing that's important about this line here is we said it's of length 5, but this line, as I move the paper, the direction it's moving in changes. So something's changed about this thing here. And that's our difference between a scalar and a vector. So a scalar has only a magnitude, only a size, and a vector has a direction and a magnitude, or a direction and a size. So one way of thinking about it is a scalar is just a length, it's just a number. A vector is an arrow, it's a length of a line with an arrow on it, okay? So the length of the line is how big it is, that's the magnitude, and the arrow tells you which direction it's moving in. And we can represent vectors like this, vector A. Now, when you're writing vectors, they need an underline. In the textbook, they'll be in bold font, okay? So vector A and vector B. If I do vector A and then start vector B at the end of vector A, then that journey I've done takes us from here all the way to over here, and that journey is what I'm going to call vector A plus vector B. Okay, so we've got this idea of vector addition, which you will have seen before at GCSE. The other thing to point out is if that there is vector A, if I draw a line, you know, this line here is supposed to be the same length and the same direction, that is still vector A. It doesn't matter where I start and finish. So it's not that vector A is the line that takes you from this point to this point. Vector A is the journey that if I start somewhere and I move in that direction for that long, then I've done a vector A. All right, so this is vector A, this is vector A, this is vector A. They're all vector A. They're not different versions of vector A. They're not, you know, vector A starting here, vector A starting here. They're all called vector A. They're all the same thing. The vector A describes the journey. Okay, so one way of thinking about the vector is a line with an arrow. Another way of thinking about the vector is a description of a journey. Go this far in this direction. If you start in a different place, you'll end up in a different place, but that's fine. You've done the same vector. Okay, you've done the same journey along the way. So we have vector A, vector B, vector C. Minus vector A is a vector with the same magnitude and the opposite direction. So travelling backwards along vector A is minus vector A. What else do we need to know here? So we can do vector addition like this. Vector subtraction, we use the fact that vector A minus vector B is the same as, well, in algebra, taking something away is the same as adding minus that amount. So we know what minus vector B means. So vector A minus vector B would be like this. If vector B is this vector here, then minus vector B would be something like that. That's vector A, that's minus vector B. So that journey there is vector A minus B. We also notate vectors like this. We tend to give vectors lowercase letters. They have to be in bold type if you're typing, and underlined if you're not typing, not word processing. Uppercase letters tend to be points. So this is point A, this is point B. This is the vector that takes me from point A to point B, and it is the vector A to B. So if I want to describe a vector taking us from one point to another, that's the notation for it. If that vector is called vector C, and I do this vector over here, if that vector has the same size and direction as vector C, then this vector over here is also vector C. It's no longer vector A to B because it doesn't take us from point A to point B. Okay. So we've got the idea of vector addition. Multiplication, if I wanted to do something like 3 lots of vector A, well, what that means is multiplication with numbers mean, 3 times 2 means 2 plus 2 plus 2. So let's do the same thing, and let's define multiplication to be repeated addition. So 3 lots of vector A, multiplying this vector by this number by this scalar, I do vector A plus vector A plus vector A. So there's vector A, add on vector A, and add on vector A. So that thing there is, the whole thing is 3A, okay? So 3A is just the vector A, but 3 times the length. So you just multiply the length by 3. And then, dividing, so vector A divided by 3, well, we're going to use that as a third times vector A. Well, vector A times by a third would be vector A, but a third of the length, wouldn't it? So vector A divided by a scalar we can deal with. So we can do a vector plus a vector. We can do a vector take away a vector. We can do a vector times by a number, times by a scalar. We can do a vector divided by a number, divided by a scalar. We can't do the other things. What does it mean to take a vector A, times it by a vector B? We don't have a definition for that, because multiplication is repeated addition. Well, how do I do a vector B, vector A many times? It doesn't make sense, because a vector A isn't just a scalar, isn't just an amount, isn't just a number. So we can't do vector A times vector B. Later on, you'll discover that there are 2 operations that we call vector multiplication, and we call them multiplication really because we haven't defined what it means to do a vector times a vector, and therefore when we come up with an operation which combines 2 vectors, we may as well call it multiplication. And there's 2 ways of doing that, and one's called the scalar product, one's called the vector product. But we're not going to worry about those, I think, in fact, not until the further maths syllabus. I might be wrong, maybe they may be on the secondary level. And the other thing that we can't do is the number 3 plus vector A. That doesn't mean anything either, because we can't do a vector plus a number. This thing is the number 3, and vector A is something that looks like that. So how do I add those 2 things together? I'm not sure. So we don't have a definition of a scalar plus a vector or a scalar minus a vector. We don't have a definition of a scalar of a vector times a vector, but we can do a vector times a scalar. We can do a vector plus a vector. We can do a vector divided by a scalar, and we can do what's the one I missed out? A vector subtract a vector. Okay. So the sort of thing that we can do with these is in example 2. And we have this sort of thing. We tend to pick a point, and we get vector A, vector C, and vector B in this case, all coming out from this point, which in this question they've called Q. And we've got point P here, point S here, and point R here. And then vector D takes us to point T. So the question is asking us, what is P to S in terms of vectors A, B, C, and D? Okay, well, the trick to these questions is make the journey, but you have to make the journey along vectors that are named. So this vector is named this vector. So from P to S, I go minus vector A plus vector C. So minus A plus C, in other words, C minus A. Okay? The next part they ask us for is for R to P. Well, we need to make the journey along named vectors, so we're going to go backwards along B and forwards along A. Sorry, I forgot to underline that. So that is A minus B, okay? Minus B plus A, and it's neater to write it that way around. If I'm going from P to T, then this is the first one where I've not got any line drawn in, but I need to make the journey from P. Oh no, sorry, we didn't have P to S. So let's put P to S in now. We have that journey is C minus A. We have from R to P, but I can't put that in because it sort of overlaps with P to S, so I'll just leave that for the moment. P to T, well, I can't go straight there because I don't have a label for that, but I can go this way, minus A plus B plus D. So B plus D and a minus A. So that one I've got now. And then T to S is this journey here. So again, I could think of it, now in this case, as minus D minus B plus C. Okay, so one option is C minus D minus B. Okay, so from T to S, I can go that way. But now I can go along this vector because that's labelled, right? So I could go minus that plus that. So it could be minus b minus d plus a. That's minus that vector plus this vector here. Okay, and then the a's would cancel out, and I'd have the plus c minus d minus b, which is the same. So either route that we go, it's the same thing, okay? This is the sort of thing that we have to get used to doing. There's several other examples, and they overlap a lot with GCSE, so it's very difficult to know exactly how much detail we need to put in. Whatever I cover, someone will be saying, oh, why didn't you do one of these examples? But I think I'll just do one or two other little bits. I'm not going to be able to cover everything here. The other advice really is this chapter's had to be split up into sections, but the sections really do all intermingle and cross over each other. So, look at the whole chapter as a whole and see what happens there. The other thing is, if you have a parallelogram, so in this question, if I tell you that this is a parallelogram, then this vector over here has to be B as well, doesn't it? And this vector here has to be A, because they're parallel, therefore they're going in the same direction, and they're the same length, because opposite sides in a parallelogram are the same length. So they must be the same vector. So that's often a helpful fact. Showing two vectors are parallel. So for example, the example they gave us is that 6a plus 8b and 9a plus 12b. Well, showing that those two are parallel, if you look at this, this is, if I take this vector here and times it by 1.5, I get this vector here. Okay, now that shows that they're parallel because if I times a vector by a scalar, I get a vector in the same direction, but with a different size. And for two vectors to be parallel and them having the same direction, that means the same thing. So two vectors being parallel means that they have the same direction. And the other little trick that we use quite a bit is this one. So we might have 3 points, A, B, and C, and this might be the vector B. This might be the vector C. The vector from B to C is minus B plus C, so C minus B. Oops. Is that vector there, C minus B. And if I put a point here in the middle and call that point P, I want the vector A to P. Oops. So I'm telling you that P is the midpoint of BC. How do I get the vector A to P? That's what I'm interested in. And the way that we do that is to say, well, I'll go from A to B, that is vector B, and then I go halfway from B to C. So halfway from B to C, and the journey from B to C is C minus B. So that sort of thinking as well. Now, unlike a lot of other areas of the textbook, I can't sort of solidify this part of this chapter into sort of simple bullet points. You've just got to look through all the questions. There's a few little techniques there. There's everything that we know from GCSE. You've got to get used to using them. As my class this year is saying, oh, it's that last question from the GCSE paper that we all hated. Yes, that's the sort of thing that happens an awful lot on this chapter. So a bit like trig identities, lots of practice is the only real way forward. That's, I think, everything we've got to say on section 11.1. Move on to 11.2.